Okay. So our next distribution, our next discrete distribution is the negative binomial distribution. So what's the first question you want to ask me, Joe? Whenever we introduce a new distribution, you have to get familiar with it and you have to ask it questions.
I think, I'm not sure if I got the order on what the parameters, or was that the second one?
Yeah, no. That's like a new girl comes to your school and you go straight for like, oh, how many boyfriends have you had? Like that would be like quite a like detailed, like, you know, or are your parents divorced or something like that. No, you just need to start from, oh, hi, you know,
how do you find the probability?
What music do you like? Or just some general stuff, first of all. What music do you like? Or just even, yeah, where do you live is kind of a good time. Oh, I live in Watford. Yeah, okay.
Oh, is it, when does it occur?
When does it occur? When does it occur? Okay, so when a binary trial is repeated until a target number of successes is achieved. So do you remember the geometric distribution? We used to keep taking our driving test until we achieved a success. And that is a logical situation for many, a logical situation that we come across many times. We have, we keep doing something until we've achieved a success. Once we've achieved a success, we don't really carry on doing that anymore. But there would be other situations where you're given a target, like say, for instance, if you're selling stuff, you'll be told, okay, your target for this month is 100 sales. Yeah. So you've got to keep ringing up people and giving them an earful on the phone until eventually, you know, you've made your 100 sales. So by badgering these people into buying your product, then you might be able to make your 100 sales. So until a target number of successes is achieved. So I would say that as a target number of sales is achieved. Until like, you got to sell 5 this week, yeah? Otherwise you're out on your own. You've got to sell 5 this week, otherwise you're out on your own. So in that sense, it's a bit like a binomial distribution. So some of the things that, and it's a bit like a geometric distribution. And so some of the things we're going to get here, these extra conditions, are the same ones as we would get in a binomial geometric situation. The events should occur randomly, not regularly spaced. So what I mean by that is when you try and get a sale, that particular call should be quite random whether or not you're going to get a success on that call or not. It shouldn't be all the morning calls. They're the ones where they're harder to get a sale. So that's why the boss has given you those calls to do in the morning, because they're the tougher ones to sell to. And then the afternoon he's giving you the easier ones so that you don't, you know, by then you'll be tired and you only want the easy one. So it shouldn't be like that. It should be all equal. The event should occur with uniform likelihood, not cluster. Events should be independent of each other. So like with the driving test, we said, yeah, but it wouldn't really be independent of each other, because once you've failed your first test, the chance of you passing your next test should really go up a bit, because you should have done a few more practices and then done your second test. So they're not really independent of each other. So we want there to be no change in the probability of success. So again, that's quite good for sales, because, you know, just because you sold someone the first call, you sold them something, doesn't mean you're going to be able to sell the second person anything, because it's just kind of independent of each other. Okay, so first thing is, when does it occur? When you're going to try something until you've got a fixed number of successes, and each goes independent of the last. What's the next thing you want to ask me to get yourself familiar with this distribution? So first question we asked was, when does it occur? We know when it occurs. What would you like to know next, to Shane?
What are the parameters?
Lovely. What are the parameters? Okay, so 2 parameters define a negative binomial distribution. So what I've got here is XR follows a negative binomial distribution. This is the probability of success on any one go. So when you call the person to ask them to buy your double glazing, you know, maybe you've only got a 10% chance of success. So that'll be 0.1. And this is how many successes you need to achieve before you can go home. So the boss says, right, once you've got 5 sales, then you can go home. Otherwise, you're just staying here. Even if it takes all night, you're just going to ring people up in the middle of the night and keep trying to sell stuff. So now some actually these are normally this way around. They're normally the other way around. They have the R on that side and the P on that side. But I don't want to get it confused with the binomial distribution. So I purposely swap them around. That's what I was taught when I was younger. You swap them around so that you don't get it confused with the binomial distribution. Nobody really cares which way around you put them. So it won't make any difference which way around you put them. But I don't ever want to get it confused. And sometimes, you know, when you're NB, your N didn't write properly or something like that, then you end up thinking, oh, it's a binomial distribution. Okay, here's the thing. There's two different ways we can define this distribution. Okay, so one way is XR is the number of goes until you've achieved your 5 successes or something like that. So, you know, you every day you have to achieve 5 sales before you can go home. And then on Tuesday you come home and then your wife says to you, oh, how many people did you have to ring today? Because she knows if you have to ring over 20 people, you're going to be in a bad mood. Yeah. So so she goes, oh, how many people did you have to ring today? And you said, oh, I had to ring like 25 people. And she goes, oh, okay. And she better make you like a really nice dinner or something like that, because you're going to be in a foul mood otherwise. So that's one way of doing it. X is the number of trials until you get your 5 successes. And YR is the number of failures until you get your R successes. So why do we have 2 different ways? Well, first of all, they're not that different from each other. So for instance, if your wife knows you've got to sell 5 units of double glazing, and if you come home and she says to you, oh, how many people did you have to call today? And you say, I had to call 28 people and I'm in a foul mood, so leave me alone. Then, okay, so she knows you had to call 28 people and you got 5 successes at the end of that, because she knows you didn't go home until you got your 5 successes. You wouldn't be home otherwise, right? If on the other hand, when you came home, she'd ask you, how many people didn't buy your double glazing? How many people called you an idiot and hung up on you, in other words? If she asks you that question instead, then the answer is obvious, because we know you had to call 28 people. We know you got 5 successes. So that means 23 people must have shouted in your ear and hung up on you. Yeah. So if she says to you, how many people hung up on you today? You'd say 23. And it's the same answer really as saying, yeah, but I sold 5 and I had to call 28 people. So that obviously means 23 people told me to bog off. Yeah. So they're obviously the same question with the same answer effectively, although the numerical value is different, but they mean the same thing. But obviously the wording of the question is different. When your wife says to you, okay, how many people told you to sod off today? That's different from when your wife says to you, oh, how many people did you have to call today? It seems more concerned, doesn't it? The other seems more like, okay, I don't care anyway. Okay, so why do we have these 2 different definitions? Well, I'll show you why we have the 2 different definitions. This is better for some things and this is better for other things. So that's why we end up having the 2 different definitions. Okay, so now we know how to define it. So in some cases, we're going to say X5 equals number of calls until 5 sales made. X5 follows negative binomial, and you haven't got much of a chance of making a sale. 0.2 is a chance of you making a sale, and you've got to make 5 sales before you can go home. So there's one way of defining a distribution. Another way of defining a distribution, which would also be a negative binomial distribution, but I'll do a different negative binomial distribution. Y3 equals number of failures until I get 3 hoops. I don't know what you call it actually. You know when you get a basketball and you get it through the hoop? I don't know what that's called. A score or a hoop or whatever. Number of failures until I get 3 hoops. So I'm only learning to play basketball. I don't really tend to get it into the hoop very often. And so I'm just measuring each day how many failures until I've managed to get 3 hoops. When I manage to get 3 hoops, I kind of celebrate, think, yay, I managed to get 3 hoops. But sometimes, you know, that's like 10 failures until I manage to get my 3 hoops. And other times it's like, you know, 8 failures, and other times it's like 15 failures until I manage to get my 3 hoops. So number of failures. So y3 follows negative binomial. The chances of me getting my hoop is say 0.25, and I need to get 3 of them. Okay, that's probably optimistic. It's probably less than that for me, probably 1.5 or maybe even 0.1. I don't know. I've never actually tried it, so it looks hard, but okay, so that's how we define it. What's the next question you want to ask me about this distribution? Devansh. We know now when it occurs. We know how to define it. We know what parameters it's got.
What does it look like?
What does it look like? What does it look like? Good question. What does it look like? Y4 follows negative binomial 0.4, 4 looks like this. Now, how do you know what it looks like? Well, to help you, what you'd want to be able to do is to find the mode. So the mode is easy to find. It's going to be Q over P times R minus 1. So Q, well, that's P is 0.4. So what would Q be, Joe? P is 0.4. What would Q be, Joe? P is 0.4. What would Q be, Joe? Joe, you're not answering me. It's like an easy question, I guess.
Oh, sorry, I thought I was unmuted. 0.6?
Yeah, 0.6. So 0.6 over 0.4, which is 1.5, times R minus 1 times 3. 1.5 times 3 is 4.5. You need to round it down. Round down. Round down to the nearest whole number. Round down. Let's just check you know how to round down, because sometimes people don't know how to round down. What's 12.2 rounded down, Het?
12.
Very good. What's 71.99 rounded down, Het? 71.99 rounded down.
17.99 rounded down.
71.99 rounded down.
72.
Did you round up?
Yeah, because you have to go down by 99 if you want to go to the other one. So it's easier to round up by 1.
Yeah, but I told you to round it down. You have to round it down. I'm just telling you to round down. It doesn't matter whether you want to round up, whether it's closer to 72 or not. You have to round down.
71.
Yeah, you have to round down. Okay, one more. 10 rounded down.
It's 10.
But is it? Could be 9. You got to round down.
Yeah, but it's 10 because it's not got a decimal next to it.
Yeah, but
So
you
it's
haven't rounded
10.0.
it down. Rounding it down means you got to go down.
So it would be 0.
No, down by 1. Down to the next number, not down to the bottom. So 10 rounded down. Some people would say the answer is 10 like you did, Het. And some people like me would say the answer is 9. And the answer is 10 and 9. 10 and 9, both answers, okay? If you've got a whole number and I insist you round it down, then you have to give me both numbers, yeah? So if I say to you round down 10, you have to say 10 and 9, okay? All right, so my mode for this was Q over P, which is 0.6 over 0.4, which is 1.5, times 3, which is 4.5, rounded down is 4. So my highest bar will be at 4. So my highest bar will be at 4, okay? Right, so there's my highest bar. My lowest bar will always be at 0 for Y4 or for Y6 or for Y10. The lowest bar will always be at 0. That's important. That's why when we're drawing it, we'd rather draw Y4 than X4. X4. We don't like that. We like drawing Y4. It's easier to draw. Yeah, it's easier to draw. Okay. All right. So there's our highest bar. So when you're drawing it, what you're going to do is you're going to start with your highest bar. You set your highest bar. Your highest bar, we know in this case is going to be 4. Then it's going to go down 3, 2, 1, and it has to go down to 0. Okay. how far across does it go? Well, the answer is it never stops. Because sometimes, you know, the guy's got to make 5 sales of his double glazing or something like that, yeah? And before he can go home. Well, that would be unfair, because sometimes he might ring people all day and still not make his 5 sales. And he might stay up all night and stay the whole next day and still not make his 5 sales. He just could be really unlucky one particular week. And so he might not get to go home for about 3 or 4 days or even a year. It's possible, you know, no, everyone he calls. So the negative binomial distribution hasn't got an upper limit. So in that sense, it's like the Poisson distribution and like the geometric distribution. They don't have an upper limit. But you can see that by about here, the bars have kind of pretty much dropped down to so close to 0, you can't even see the difference anymore. Yeah, they're so close to 0. They're not 0, but they're so close to 0 that you can't, those probabilities would be minuscule. You wouldn't be able to see them on my drawing or anything like that. So how do you find out where they are? Where do you have to go up to before it drops down? Well, there's a sort of rough way of doing it. What you do is you've already found the mode, which is 4. You divide that by p. So you divide that by p, which is 0.4, divide it by 0.4 and add on 5. So that gives me 4 divided by 0.4. So 4 over 0.4, like that. And then plus 5. And then plus 5 to that. So that gives me 15. So 15 is going to be roughly how far my bars need to go to. So by about 15. And you can see it's not accurate because these bars actually carry on past 15. Yeah, you can see the bars carry on past 15. But it's just a rough idea for my sketch. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now I'm going to stop with my diagram. That's going to be as far as my diagram goes. So when I need to sketch, if you can sketch a distribution, it's going to make later things that you will need to do with distributions, such as testing, a lot easier. If you can't sketch a distribution, testing is really hard. If you can sketch a distribution, testing is really easy. Okay.
So the plus 5, is that a constant?
Yeah, it's just plus 5, always plus 5. So it's mode divided by p plus 5, and it's only going to give you an approximate answer. If you want to get a more accurate answer, it's more like RQ plus square root RQ plus 3 lots of square root RQ all over P plus 2, which is too complicated. Nobody wants to do that. Yeah. So this is just a rough, it's quick. It's a quick, rough way of getting an answer. Okay, and it's only for our sketch anyway. Really, we don't even need to show where our upper value goes. Nobody's going to care where our upper value goes because there is no upper value. It doesn't stop, so it carries on and on forever. But it's just to help us to draw our sketch. Okay, so there's our sketch. So then I told you that this is easy to sketch. Y4 is easy to sketch. What if you want to sketch X4? So remember, Y4 is the number of failures until you get to the 4th success. You might be really lucky. You might have no failures. You might just go success, 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 success. And you had no failures and you got your 4 successes. Yeah, it might just be luck. You might call it skill. I'll call it luck. Yeah. X4 is going to be the number of goes until you got your 4th success. Until 4th success. Well, if you did it with no failures, then your number of goes would have to be 4. If you did it with 5 failures, then your number of goes would have to be 9. So actually this and this are only separated by 4 units along the x-axis. So slide that 1, 2, 3, 4 to there. And that's what X4 looks like. Can you see the green one is what X4 looks like? This is our graph of X4. The green one is our graph of X4. It's the same as Y4, but shifted to the right by 5. So if anyone asks me to sketch X4, I'm going to sketch Y4 and then just shift it to the right by 4. Okay, let's have another go. Okay, so this is Y4, but this time our distribution is 0.4, 4. What was our distribution last time? It was 0.4, 4 last time. I don't know what that is. So that looks like nonsense. Okay, let's do this one. Y4 is negative binomial 0.75, 4. Okay, so this time it's still n is 4, but the probability has changed to 0.75. And you can see that that's pushed the graph to the left a lot. It's pushed the graph, shunted it all up on the left-hand side. doesn't go very far to the right. Okay, so how do we work out our mode again? We have to do Q over P, so 0.25 over 0.75 times this minus 1, times this minus 1, times 4 minus 1, times 3, and then round it down. Can you stick that in the calculator for me? 0.25 over 0.75 times 3, and then round it down. Make sure you round it down. And give me your answer, Joe.
I haven't got my calculator.
Okay, I'll help you. 0.25 over 0.75 cancels down to a third.
1.
Oh, Joe.
You said just to calculate that, so it's a third times
And
3.
round it down.
Oh, 1 or 0.
Yeah. So 1 and 0 are our mode. Can you see 1 and 0 are our highest bars? In fact, they're quite high. How far is this going to go? Well, the mode divided by P plus 5. What was our mode? Our mode was 1. I'm going to count the higher of the two. Divided by P. What was P? It was 0.75. Divided by 0.75 plus 5. 1 over 3/4 is 4 over 3 plus 5. 4 over 3 plus 5 is 6 1/3. 6 1/3. Let's call it 7. So my highest bars are going to be at 0 and 1, 0 and 1, and then it's only going to go as far as 7. So there are no lower bars to the left, so because you can't go below 0. So then 2, 3, 4, 5, 6, 7. And so there's what my sketch looks like. There's what the actual graph looks like. If I wanted to figure out what x4 looks like, so this is y4. If I needed to figure out what x4 looks like, x4 follows negative binomial 0.75 comma 4. What would I do to this sketch? Asking to Shane.
So could you repeat the question?
Yeah, so we've sketched y4, but now if they ask me to sketch x4, what would I need to do to this graph?
You have to shift it.
To the right? By how many? To the right by 4. Why? Okay, so this is something you're very good at because the probability of success is quite high. Yeah, so this is something you're very good at. Maybe it's snooker. Maybe you're really good at potting reds in snooker. Okay, so how many goes do you take until you've potted 4 reds? Okay, so I say to you, right, how many failure, like you've got, I don't know, it's like they're just lined up. It's not like a proper game of snooker. They're just lined up. The balls are lined up everywhere, and you have to pot 4 reds. And if you miss a red, you just carry on. You just have another go, and you have to pot 4 reds. Yeah. And then I say to you, how many failures did you get until you spotted 4 reds? And this is the graph. This one, the blue one, the dark blue one, is the graph of how many failures you get. Because if you say to me, oh, I did it with no failures, it means that you got success, 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 success. You potted, 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 potted. You got it no failure. But if I say to you about how many goes was that you had, you'd say, well, I had 4 goes, but each one was a success. So the difference between how many failures you had to get 4 successes and how many goes you had to get 4 successes is always just 4. You just increase it by 4. If you say to me, oh, I had to pot 4 reds, and I say, oh, okay, Shane, you're quite good at that. How many goes did it take you? You say, oh, it took me 6 goes. It took me 6 goes. And then I said, so how many failures did you have? You'd say to me, well, come on. If I had to pot 4 and it took me 6 goes, you know how many failures I had. It's easy. You just minus 4 from it. Yeah. And if you say to me, oh, I had to pot 4 reds, and I say, okay, how many failures did you have on your way to potting 4 reds? And you said, well, I had a bad day, so I had 6 failures before I potted my 4 reds. And then I say, oh, so how many goes did it take you? You say, come on, if I had 6 failures before I potted my 4 reds, then that's 10 goes it took me to pot my 4 reds, obviously. Yeah. So they're just 4 apart from each other. The number of goes you had and the number of failures you had are just 4 apart. This is the number of failures you had before you potted 4 reds, and then just shift it across by 4, and that's the number of goes you had before you potted your 4 reds. Okay, so here's another one, binomial 0.5, 8. So how would I find the mode for this? How would I find the mode for this? Asking that to Het.
Would it be 0.5 over 0.5 times by -1?
Yeah, 0.5
is,
divided by 0.5 is just 1, isn't it?
Yeah, it's 1, and then r minus 1, which is 7.
So 1
it'd be
times
7 and 6.
7. Say that again?
So the answer would be 7 and 6.
7 and 6. So what you're saying is the mode is 7 and 6. So there's 6 and there's 7. And those are the mode on the graph, aren't they? They are the highest bars on the graph. So absolutely right. Well done. So that's the mode. If you want to sketch it yourself, if you don't have a sketch of it yourself, you know that 7 and 6 are your mode. So 7 and 6 are your mode. 6, 7. You know that from 6 you've got to go 5, 4, 3, 2, 1, and 0. And by 0, the properties are going to be quite small. If you want to know how far to go, what you're going to do is you're going to do the mode. Let's choose the larger of the mode, divided by p, divided by 0.5, and then add 5. So 7 divided by a half is 14, plus 5 is 19. So this is going to go quite far from 7 to 19, which is I don't want to draw that all properly, so I'm just going to do it quickly. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And so that's what my sketch of the graph looks like, yeah? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it'll go up to 19. It carries on past 19, but by 19, the properties are quite small. And so that's what you see here. That's exactly the graph you see here. Okay, so that's the graph of y8. What if someone wanted to sketch x8? x8. What would they have to do to this graph to sketch x8, Devonch?
Shift this by 8 units, right?
Shift it right by 8 units. So that's going to be to about there. And so that's the graph of the number of goes until you've got 8 successes. So obviously you can't get your 8 successes in 6 goes. That's not possible. Oh, how many goes did it take you to get 8 bullseyes? Oh, yeah, I did it with 6 darts. No, you didn't. That's not possible. Yeah. The least you could do it in is 8 goes. And obviously it could take you a lot of goes to get 8 bullseyes. Yeah. You might have to throw like, 20 darts before you get your 8 bullseyes or something like that. If it's the number of failures, then it would look like that. 0.5 as a chance of scoring a bullseye seems incredibly high. So I'm going to assume the bullseye on this dartboard is that big. Yeah. Yeah. What does this look like? Y12 follows negative binomial 12, 0.5. So what you see is when you've increased n to 12, that sort of made the graph flatter and wider. So as you increase the number of successes you need before you can stop, it widens the graph. It makes it a lot flatter and wider. Whereas increasing p shifts everything to the left, and decreasing p shifts everything to the right. So again, we can do our same thing. Our mode is going to be 0.5 q over 0.5 p times n minus 1 is 11. So our mode is going to be, well, 11 and then rounded down. So 10 and 11 are going to be our mode. And then we can do mode divided by 0.5. So 11 divided by 0.5 would be 22 plus roughly 5. So 27 would be roughly when it stops, around about there. And then that will be enough to sketch it. And then if somebody asks us, what does x12 look like? What we would do is take this whole graph and shift it to the right by 12. So 10, 11, 12 is there. So shift the whole graph to the right by 12. Okay, let's have a go at drawing one ourselves. So we've got y5 follows negative binomial 5, a third. So I need to sketch this. So let's start off with a grid. We'll try and draw it reasonably decently. But it's never going to be, it's still always going to be a sketch. It's not going to be like those ones you saw there. Okay, what should I do first to help me sketch this, Joanna?
Find the mode.
So that's 2/3 over 1/3 times 4 and then rounded down. So that's 2 times 4 and then rounded down. So that's 8 and then rounded down. So that's 8 and 7. So 8 and 7 are going to be my highest bars. So 7 and 8 are going to be my highest bar. Okay, now I've got to go to the left only as far as 0 because you can't go below 0. So 6, 5, 4, 3, 2, 1, 0. On the right hand side, I've got to go to 8 divided by a third. 8 divided by a third plus 5, which is 24 plus 5, which is roughly 29. So I'm going to go 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and it's going to go quite far to 29. So there's my sketch of what that distribution looks like. It's actually quite poor, that sketch, because those bars need to tail off a bit more slowly, like that. And it needs to go further to the right, but I didn't leave enough room to go far enough to the right. Okay, let's have a sketch of this one. So x2 follows negative binomial a fifth comma 2. Let's try and draw this a bit better than we drew the last one. Okay, what do I do first, Tashain?
We find the mode.
What would the mode be?
It's fifth over fourth, so quarter mod 2. So it's half rounded down.
Hold on, it's Q 4 over 5 over P 1 over 5 times this minus 1 times 1.
Oh, right. So 4 rounded down, so 3 and 4. 4
and 3, 3 and 4, 5, 2, 1 and 0, 0, 1 and 2. Okay, how far should I draw my bars? How far should I go with my bars? Asking that to Hep.
What do you mean? How far?
How far? I need to draw the bars on the right hand side. How far should I go on the x-axis? What range should I use?
You could go up to.
You can't make it up. You have to use what I've been teaching you so far.
Oh, so you have to find the mode. So when it be Q.
No, we found the mode. The mode is 3 and 4. Now you need to find the range. Devonch, tell him how to find the range.
So that's 4 over 3 or 4 over 1 over 5 plus 5.
Plus 5. So that's 25. So I need to go as far as 25. That's not the actual range. So that's just rough. So we won't write that down. So 25.
So I forgot. Why do you add 5?
It's just a rough rule. It's just a rough
so it's always 5.
Yeah, always 5. It's just a rough rule. It's not even accurate. Yeah, it's not even accurate. It's just a quick way to help you draw your sketch. Yeah, I showed you the quick way, the correct way. The correct way is QR plus 3 root QR over P plus 2. But nobody wants to do that. Nobody wants to do that because it takes too long. Yeah, so we just do it a quick way. So we're going to go as far as about 25. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, again, I didn't quite manage to leave enough room for it, but it's kind of a reasonable sketch of what it looks like. Okay, so we now know how to draw it. We know how to draw it. That's important because only if we know how to draw it can we understand some of the more complicated things that are going to arise from this. Okay, right, so we've learned when it occurs. We've defined it, figured out what parameters you need to define it, and we've looked at what it looks like. We've sketched it. Now that we've defined it, we've sketched it. What's the next thing you'd like to know, Joe?
How to find the probabilities.
How to find probabilities on it. We don't even know how to work out any probability. We've drawn the graph with all the probabilities on it. There's a graph with all the probabilities on it, but we don't actually know how to find any of these probabilities. Yeah, these probabilities, the probability of 6 and 7 here are about 0.1, but we don't know how to work any of those out. So let's work out, how do we work out the probabilities? Well, the negative binomial distribution is formed from the binomial distribution. So when we're calculating probabilities, we do just use the binomial distribution. Okay, so how do I find probabilities? Well, firstly, it depends on what you were defining. were you defining X as the number of goes until you achieved your 4 successes or how many successes you needed? Or were you doing the number of failures? If it was the number of failures, then the way you're going to work out the probabilities is different. If you were counting the number of trials, the number of goes, then the way you're going to calculate your probability is different. So we're going to stick to this one first. When you're working out probabilities, I would probably use this method when I'm working out probabilities. Whereas when I want to sketch it, I sketch Y6 rather than X6. And then I shift it to the right by 6. So I start from Y6. Going from Y6 to X6 is easy. It's easy to go from one to another. It's really easy to go from one to another. Okay, so here we've got a distribution. X6 follows a negative binomial distribution with a success rate of 0.8, and I need to get 6 successes before I can stop. So maybe this is me ringing up people who've already been burgled, and I'm ringing them up because what I've done is I've bribed the police. I've bribed the police department to look, when somebody's burgled, can you give me their phone number? And then I'll ring them up and say, oh, would you like to buy my burglar alarm? I'm selling burglar alarms, yeah? So every time, whenever the person gets burgled, I say to the policeman, look, you just give me their phone number. I'll slip you like tenner. You give me their phone number, and then I can ring them up. They're more likely to buy my alarm system. If I just ring up people out of the blue and say, oh, would you like to buy an alarm system? They'd say, why are you ringing me up, you idiot? And then they'd also say, I don't want your crappy alarm system, yeah? It's a really crappy alarm system. Basically, it's a Yorkshire Terrier in a box. Just send them a Yorkshire Terrier in the post. That's it. That's their alarm system. Okay, so right, every day I need to sell 6 people this alarm system. But luckily, I've got a huge chance of success. There's a 0.8 chance of me, any person I call, them choosing to buy it. Why? Because they've just been burgled. Why? Because I've bribed the policeman. So I'm only calling people who've just been burgled. Okay. So it says, find the probability that I get my 6th success on my 8th go. Okay, so you lot are also in the office, but your job isn't sales, yeah? Your job is admin, yeah? Your job is admin. Your job is to just, arrange the installers and do those kind of things, yeah? And every day, I go home after my 6th sale is made. That's the deal I made with the boss. Once I've made my 6th sale, I go home, okay? So, and for fun, because your job is really boring, what you decide to do is you decide, let's have a bet between you lot, yeah? And a het bet that I'm gonna get my 6th out on my 8th go. And Shane bet I'm gonna get my 6th out on my 10th go. And Devansh bet that I'm gonna get my 6th out on my 6th go. He was incredibly confident in me. He says, this guy's gonna get his 6th sale straight away on his 6th go. Every single person he rings up is gonna say success. And Joanna was completely against me. She said he's going to get his 6th sale on his 15th attempt at calling somebody. Okay, so you lot are all wondering, okay, which one of you is going to win the bet? You've got some money riding on every day. You have some money riding on it, and so in particular, Het said I'm going to get my 6th out on my 8th go. So we want to work out the probability that Het's going to win the money, because you all put in a tenner. And whoever wins, they win the money. So, okay. So, find the probability to get my 6th. Imagine when I've got my 5th success. Imagine on the 7th go, I've already got 5 successes. So imagine on the 7th go, I've already got 5 successes. How's Het going to be feeling now? Yeah, so in the morning you come in, I ring somebody up, they say, oh no, I don't want to buy the double glazing. So people like Joe's feeling really good. Yeah, see, nobody's going to buy his glazing today. Oh, it's not a glazing, is it? It's an alarm system. Whoops. Okay. Oh dear. Okay, that's no good. Ringing up people who've just been burgled and saying, do you want to buy double glazing is probably not a good idea. Okay, and then the second person says, yes, I'll buy it. And so now people think, oh, maybe it's going to be better today. And then the third person says, I'll buy it. And then the fourth person says, I'll buy it. And by the time I get to the 7th person, 5 people have already bought it. So out of 7 goes, 5 people have already purchased. Okay, and Het said he's going to get, on the 8th go, he's going to get his 6th sale. Het said on the 8th go, he's going to get his 6th sale. So we're already up to 7 goes. This is the 7th call I've made, and I've made 5 purchases. I've managed to make 5 sales so far. Het, how are you feeling about winning the money today?
Could you repeat the question?
Het, how are you feeling about winning the money today?
No, I mean what you just said before that.
Okay. All right. So you bet that it was going to take me 8 calls to make the 6 sales that I need to make before I can go home.
Yeah.
You bet that. Devonch bet I was going to make the 6 sales in 6 calls. So he was really optimistic, but he's obviously turned out to be wrong when the first caller said no. First caller said, no, I don't want to buy it. And so he'd automatically lost already. So he's given up. He knows he's going to lose. Yeah. And you'd bet that it was going to take me 8 calls to make my 6 successes. Shane had bet it was going to take me 12 calls to get my 6 successes. And Joanna had no faith in me at all. She said it was going to take me 15 calls to make my 6 successes. So imagine at some point I've made 7 calls so far. And that's resulted in 5 sales. So I've made 7 calls already, and I've made 5 sales. Remember, your bet was by 8 calls, I'll have made 6 sales. Now I'm picking up the phone to my 8th potential customer. What are you thinking your chances are now?
It'd be a 50-50 chance.
That's nonsense. How can you talk such utter nonsense? What are you thinking right now?
Because like,
you put money on me getting my 6th sale on my 8th call, and then I go
yeah,
home, right? We're on 7 calls so far. I've made 5 sales. I'm ringing up my 8 people. Tell me the nervous excitement in you.
you'd probably be a bit nervous.
Not me, you. Stop right.
Yeah, I'd probably be a bit nervous because
Why?
it's like the last call.
It's not the last call. It's not the last call. I might call 20 people today. It's only the last call if I make a sale on this call.
Yeah, it's the last call if you make a sale and like I'm about to
Okay, hey, you completely flopped that. What you were supposed to say was, I'm excited because if you make a sale on this call, it means I've won the money and I'm going to have loads of money when I go home tonight and I'm going out partying. Yeah, that's what you were supposed to say. Okay, so this is easy to work out. This is easy to work out. Out of 7 calls, the probability that I've made 5 sales is easy to work out. X follows binomial 7, comma, what was the probability of success? It was 0.8. It was 0.8. And we want the probability that X is 5. So that's 5 sales out of 7 calls with an 80% success rate. Yeah, that's 5 sales out of 7 calls. Easy to do. Yeah. So now I just go to my calculator. I go to distributions. I go to binomial distribution. I don't want CD, I just want PD. So binomial PD. Then I don't want list, I just want a single number. So I choose variable. I want X is 5 on binomial 7, 0.8. I want X is 5 on binomial 0.7, 0.8. And there it's worked out that probability for me, 0.275. So that's the probability that we would be up to this stage. Now I'm making my 8th call. So far we've got 7 calls and 5 sales. Now I'm making my 8th call. What's the chances that that 8th call will be a success, Het? What's the chances that 8th call will be a success, Het?
It would be 1 in I'm so confused, to be honest with you.
Okay. What am I selling, huh?
You're selling from security kind of camera thingy to someone.
Alarms. I'm selling alarms.
Alarms. Yeah,
Okay.
you're selling an alarm to.
How
like,
many
you're
alarms
calling-
do I have to sell each day before I can go home?
You need to sell 6.
Okay. What did you bet on how many people I was going to have to call before I could go home?
I said 8.
Okay. When I call somebody, what's the probability that they'll buy the alarm?
0.8.
Why is it so high? Normally, if you randomly call people and you ask them to buy an alarm, they'll say no, get lost. You'd only have like a 10% chance or something like that. It would be 0.1. Why is it so high? What's going on here?
It's like you already called 7 people and they said, yeah. 5 of them said yeah.
No, you're talking nonsense. I bribed the policeman to tell me when people have been burgled. And I've got a big list of all the people in the country who've been burgled. Yeah. So all the people who got burgled in the country over the last week, I've got a big list of them. I'm calling people who've been burgled and asking them if they want a burglar alarm. Haven't you seen the advert on TV where the lady calls up and she calls up the company and she says, "Oh, I want a burglar alarm," and they go, "Have you been burgled recently?" And she goes, "Yes." And then she goes, "How do you know I've been burgled recently?" And the lady goes, "Oh, because I bribed the policeman to tell me." Haven't you seen that advert on TV? It's on TV all the time now. About the alarm thing. Because there's loads of burglaries taking place, so people are getting like loads of alarms and stuff. Oh yeah, that's a good point. Yeah, Mena said everyone's at home, so there aren't any burglaries taking place. So when I ring the first person, what's the chances that they're going to buy the alarm?
When you ask the third person.
The first person.
Oh, the first person is 0.8.
Yeah. Let's say the first person did or did not buy the alarm. Doesn't make any difference. When I ring the second person, what's the chances that they're going to buy the alarm?
0.8 again.
Lovely. When I ring, let's say I've made six sales so far. So I've made 5 sales so far. When I ring, and I've called 7 people so far. When I ring the 8th person, what's the chances that they will buy?
0.8.
Yeah. So what we're going to do to work out this probability is we want the probability that you get your 6th sale on your 8th go. So we're just going to go back one. We're going to say, right, let's imagine by 7 goes, you've got 5 sales, just one away from the target. So 7 goes, you got 5 sales. Well, 7 goes, you got 5 sales. That's easy. That's a binomial distribution. There's a probability of being in that situation. Now, what's got to happen on your 8th call? On your 8th call, you've got to make a sale. So you just got to times that by 0.8. So it's that times 0.8, that number times 0.8 equals, oh, whoops, I was in the wrong mode. Menu 1, 0.275 times 0.8 gives me, well, it gives me 0.22 is my chance of going home after 8 calls. 22% chance I'll go home after 8 calls. Okay, so this is how it works, right? We want the probability, so the probability of success is 0.8. We want the probability that the 6th success happens on the 8th go. So that means on the first 7 goes, there must be 5 successes, which is binomial. So we can work that out. That's just binomial distribution like that. 75.2 to the 0.8 to the power 5. And then, so that's the first 7 trials have got 5 successes. Now on the 8th go, that's got to be a success. So now on the 8th go, the one final 8th go has got to be a success. And so that's how you achieve it. To get your 8th success to get your 6th success on your 8th go means that you can't have got 6 successes before 8 goes. So somewhere before 8 goes, say at 7 goes, you must have still only been at 5 successes. To get your 6th success on your 8th go means that on your 7th go, you must only have been at 5 successes, because if you'd already been at 6 successes, then you wouldn't get your 6th success on your 8th go. And you've only been at 3 successes, then you can't get it on your 8th go. So to get your 6th success on your 8th go means that on the 7th go, you must have had 5 successes. Well, that's just binomial, so we can work that out. And then we just need to make sure that the final go, the 8th go, is a success. Okay, let's have another go. So this is a different distribution. This is trying to score a bullseye, yeah? But it's hard to score a bullseye. You've only got a 30% chance of hitting the bullseye, but you've only got to get 2 bullseyes. Once you've got 2 bullseyes, then you've won, yeah? Then you can go home, then you're finished, yeah? So it's the number of goes until you get 2 bullseyes. We want to find out the probability that it takes you 5 goes to get 2 bullseyes. So we want the probability that you'll get your 2nd bullseye on your 5th go. It takes you 5 goes to get 2 bullseyes. So you get your 2nd bullseye on your 5th go. Go back 1 from there. Go back 1 from there. Tell me about the 4th go. Tell me about the 4th trial. How many successes had you achieved by the 4th go, Devansh? You've got to get your 2nd success on the 5th trial. Just go back 1. Just rein it back 1 from there. By the 4th go, how many successes must you have got?
1.
Yeah. So 4 goes, 1 success. X follows binomial 4, 0.3, 4, 0.3. And we want probability of 1 success. Probability X equals 1. So we just go back 1 from here. 1 success out of 4 goes. So we just go back 1 from there. So menu, go to the binomial distribution, go to binomial CD again, binomial PD again, which is number 4, binomial PD. I want to work out X is 1 on binomial 4, 0.3. So I choose variable. I choose X is 1. I choose binomial 4 and 0.3. And that works out to be 0.4116. 0.4116. Now, that's only got me 1 success out of 4 goes. What's got to happen on your 5th go? What's got to happen on your 5th go? You've only got 1 success out of 4 goes. What's got to happen on your 5th go, to Shane? Shane?
Yeah.
So far, our job was to get our 2nd success on the 5th go. That was our job. We've just gone back 1 from there. So we've gone to 4 goes and we've only got 1 success. Our job is to get our 2nd success on the 5th go. So far, we're at the 4th go and we've got 1 success. That's not 2 successes. Our job is to get 2 successes by 5 goes. Yeah. So far, we're at 4 goes and we've got 1 success. This is the probability so far. What's got to happen on the 5th go? We're at 4 goes, we've got 1 success. What's got to happen on the 5th go?
We need another success.
And what's the probability of that?
0.3.
So you just need to times this by 0.3. And then on your 5th go, you've got your 2nd success. And so you just times that by 0.3. So store that as X. And then go back to menu 1 and then do 0.3 times X. Gives me 0.12348 is my probability. So every time you want to work out a probability, this is 4th success occurs on 7th go. Yeah, this is 4th success occurs on 7th go. You've got to go back 1 from there. You've got to say, right, so that means by my 6th go, I should have had 3 successes. Okay, here we go. Imagine you're a parent, but you're a lazy parent, right? So you're a lazy parent and you only like to be there for the glory bits, for the bits when your child does something really well. So for the bit when your child gets their A-level results and they're all A's, you want to be there. But if they get really bad grades, you just don't want to be there, yeah? So what you do is you phone your partner and you say, right, what's got to happen today? And you say, oh, well, he's taking part in a rifle range tournament. And he has to get 4 successes within 7 goes in order for him to qualify for the championships. He's got to get 4 successes he's got to get his 4th success on the 7th go. He's got to get his 4th success on the 7th go in order for him to qualify for the championships. So you say to your wife, right, tell me just before that's about to happen. If it's about to happen, you tell me just before it's about to happen. Call me and I'll be there. I'm only like 2 minutes away. I'll be there in a second. Yeah, I'll be there in a second. But I don't want to be bothering watching him because he's boring watching him shoot and it's boring watching him do everything. I hate him. But I have to be there when the glory bits are there. So what your wife will do is when you get to, he only wants to know if you get your 4th success on the 7th go. That's what he's interested in today. So what the wife has to do is she has to phone him if on the 6th go you're at 3 successes. If you're at 3 successes on the 6th go, then the wife phones him, says, right, it's the 6th go. He's got 3 successes. That means that if on the next go he gets that final success, then he will have achieved his 7th success. He will have achieved his 4th success on the 7th go, which is what you wanted. Yeah. So 6 go 3 successes is x follows binomial 6, 0.65, 0.65. We want property x is 3, which we can work out on the calculator. And that 6 go 3 successes, to make the 7th go the 4th success, we just multiply it by 0.65. So then we multiply this by 0.65, and that will give us the probability that we want. Probability that x4 equals 7. Okay, so a fairground game involves throwing hoops over a stick. It's quite easy to do. In fact, the chance of getting a hoop over a stick is 0.8. You need to get 6 hoops. So you need to get 6 hoops to land correctly in order to win. So this is the crucial bit. You need to get 6 hoops. You need to get 6. Oh, I've hidden it now. You need to get 6 hoops in order to win. Okay. John covets the teddy. It's probably only worth £5, but to him it's easily worth £25. It costs £2.50 per throw. What is the chance that he takes 8 throws to win the teddy? Okay, you have to get 6 hoops. So x is going to be the number of goes until the 6th hoop. The 6th hoop. Why? Because the 6th hoop means you won the teddy. The 6th hoop means you won the teddy. Okay. So x is the number of goes until you win the 6th hoop. Okay. X follows a negative binomial distribution. The probability of you getting a hoop is 0.8. 0.8. Again, 0.8. And we want to get 6 hoops. So it's x6 follows negative binomial 0.8, 0.6. So that's you've got to get to the 6th success, then we can stop. Once you've got the 6th hoop, then you can stop. Then you can then you've got the teddy. You can go home. Once you've won the teddy, you can go home. Okay. We want to find the probability that it takes him 8 throws. So we want to find the probability that x6 equals 8. We want to find the probability that on the 8th go, finally that sixth hoop lands over the skittle and he wins the teddy. Yeah. Remember, he's your son, but you hate watching him do anything. He just annoys you. So you only want to be there for the last moment when he's about to achieve the goal that's set out. Today, the goal that's set out is he has to get his 6th hoop on the 8th go. So you tell your partner, right, I don't want to be there while he's doing all the other hoops. He'll just annoy me. He throws like a girl. He just no, that's sexist. He throws like a dyslexic. No, that's not even right to say that. He throws like an idiot. And that's probably allowed, isn't it? Okay. He throws like an idiot. I don't want to watch any of him throwing and stuff like that. You just tell me just before it's about to happen. When it's about to happen, then I'll come in, watch him do the last throw, and then I'll say, oh, son, you know, I'm always there to support you. I'm always there when you achieve something. See, and then, so take me back one before there. Take me back one before there. Just before the 8th go, he needs to get the 6th hoop on the 8th go. Take me back one before there, Joanna. Where are we at so far?
You haven't got the 8th success yet.
That's not a very good job of taking me back. Take me back just before it's about to happen. What's happened so far?
He's got 7 successes.
No. He needs to get 6 success on the 8th go. He needs to get the 6 success on the 8th go. But it's just about to happen. Where are we now? Just before it's about to happen.
Oh, he hasn't got the 6th success yet. He's on the
Don't tell me what he hasn't got. Tell me what he's got.
5 successes.
And how many goes has he had?
7.
Okay, well that's easy. X follows binomial 7, 0.8 because you said he's had 7 goes. And we want property X equals 5. You said he's got 5 successes so far. Can my calculator work this out for me? It sure can. I will go to menu. I will go to distribution. I will say binomial PD. I will say, oh, I've typed in CD. I'll type in binomial PD, which is 4. I'll type in variable. I'll say I want X is 5 on binomial 7, 0.8. And once I've typed those in, it will work it out for me. There you go. It's worked that out for me. It's 0.2752512. Right. So that's the moment before it happened. What has to happen next, Joe? This is the moment before. He's had 7 goes and he's only got 5 hoops so far. And we need him to get the 6th hoop on the 8th go. What's going to happen on the 8th go, Joe?
He's going to get his 6th success.
He's going to get his 6th success, which means there's a 0.8 chance of that happening. So times it by 0.8, and then that will give us the property we need. Store that as X, menu 1, 0.8X, gives me 0.22, roughly. So the probability that he will get his 6th success on the 8th go is 0.22. 6 success on the 8th go is 0.22. Okay, so we've worked that out. Okay, a fairground game involves, so it's the same game. You're throwing the hoops over the 6, 0.8 chance. You need to get 6 hoops to win the horrible stuffed teddy. It costs £2.50 to throw. What is the chance he spends more than £20 to win the ugly teddy? So this is X, X6 equals number of goes until he wins the teddy. He gets 6 successes. He gets 6 hoops, wins the teddy. Okay. X6 follows negative binomial. The chance of winning is 0.8 and we need to get 6 hoops over the thing. Okay. Now it says find the property that he spends more than £20. Now every go he takes costs him £2.50. So that means we're looking at him spending, well, 8 goes. 8 goes would cost him £20. We want the property that would take him more than £20. So we want the probability that he takes more than 8 goes. So X6 is greater than 8. So more than 8 goes means more than £20. If it takes him more than 8 goes to win this teddy, then he spent more than £20 to win this teddy. So we want to work out that property. Now, this is going to be a problem. This is going to be a huge problem because this is, for something like this, we would want a cumulative probability distribution. But we don't have a cumulative probability distribution because the cumulative probability distribution is on the calculator, but it doesn't have negative binomial on the calculator. The cumulative probability distribution is on the tables. But the tables don't have the cumulative negative binomial distribution. They just have the cumulative binomial distribution. So what are we going to do? Well, it's kind of a bit annoying, but at the moment, I'm going to say what we're going to have to do is we're going to have to work out, well, I mean, theoretically, you could be there all day trying to win that teddy. You could have had 20 goes and still not won the teddy. You could have had 25 goes and still not won the teddy. Yeah. So what we're trying to do here is we're trying to work out the probability x6 is greater than 8. Well, that could be 9, 10, 11, 12, 13, 14, right the way up to infinity. So what we have to do is you have to work out 1 minus probability x6 is less than or equal to 8, which is 1 minus probability x6 equals 1 plus probability x6 equals 2 plus probability x6 equals 3 plus. Can you get your sixth hoop on your first ever throw? Is that possible? On your first ever throw of a hoop, can you get your sixth hoop on your first ever throw? No, so I've written nonsense there. You can't get your first. X6 cannot equal 1. X6 can, it only starts from 6. Doesn't start from 1. Y6 starts from 0. So probability x6 equals 6 plus probability x6 equals 7 plus probability x6 equals 8. Okay, so that's all of these. X6 equals 6, x6 equals 7, x6 equals 8. It can't equal anything. It can't equal anything less than that. It can't equal like x6 equal 5 or x6. That couldn't exist. That's not possible. Okay, how do we work out the probability that x6 equals 6? So that means he got his sixth go on. He got his sixth hoop on his sixth go. Well, I don't even need to use anything to work that out. That's easy. That's just 0.8 to the power 6, because you have to get hoop, 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 hoop. That's that one. So that's just 0.6. That's just 0.8 to the power 6. What about this one? Well, this is negative binomial. He gets his sixth hoop on the seventh go. So we don't know where the failure was. The failure could have been on the first go. The failure could have been on the second go. The failure could have been on the sixth go. It could have been on the fifth go. We don't know where that failure was, but we know there was a failure there somewhere. What we could do is we could say, right, we know that we could rein back 1 from here. So we know that he got his sixth hoop on the seventh go. So one before then, he was on his sixth go, and he must have only had 5 hoops by that stage. So x follows binomial 6, 0.8, and we know probability x equals 5. We know that at that point he should have had 5 hoops. By the sixth go, he should have had 5 hoops. That way he can get his sixth hoop on the seventh go. Okay, so let's work that out. Stick it in the calculator. And binomial PD. Binomial PD is 4. And we want to choose variable. We want 5 on binomial 6, 0.8. That gives us our answer, which is 0.393. And then we need to multiply this. We need to multiply this times it by, okay, so we've gone to the sixth go, and he's got 5 successes. So on his seventh go, he has to get that next success. So times 0.8. So times that by 0.8. So store that as x. Menu 1, 0.8x gives me 0.3146 is that one. And then this is right, he gets his sixth go on he gets his sixth success on the 8th go. So again, wind back 1 from there. He gets his sixth success on the 8th go. Go back 1 before there. He was on his 7th go. How many successes must he have had at that stage? It must have been 5. So binomial 7, 0.8, and he must have had 5 successes. X equals 5. And then after that, we're just going to multiply it by 0.8. So after that, we're going to multiply it by 0.8. So go back to my distributions, type in binomial variable, type in x is 5 on binomial 7, 0.8. That gives me 0.275. Store that as x. Go to mode 1, type in 0.8x, and that gives me 0.22. Okay, so it's 1 minus this plus this plus this is my answer. And that was a lot of calculation to get to that answer, a lot of working out to get to that answer. We're going to learn a quicker method for doing that in a second. We're going to learn a quicker method for doing that in a second. Okay, what's the chance he spends £25 and still doesn't manage to win the teddy? So we said it's easily worth £25 to him, but what if he spent £25 and he still hasn't won the teddy? So that's x6 equals number of goes until 6 success. 6 success means he's won the teddy. x6 follows negative binomial 0.8, 6. And we want the probability, well, £2.50 a go. If you've had 10 goes, then you spent £25. And if you still haven't won it, it's going to cost you more than 25 cents. So x6 is greater than 10. We want the probability it takes you more than 10 goes. Well, to work that out, what we're going to have to do is we're going to have to do 1 minus probability x6, 1 minus probability x6 equals 6 plus probability x6 equals 7 plus probability x6 equals 8 plus probability x6 equals 9 plus probability x6 equals 10. We're going to have to work out each one of those probabilities individually, add them up, and then do 1 minus it. That's going to take us all year to do that. So we need a better way of working these out. We'll figure out a better way of working these out. Okay, so we've worked out how to work out probabilities, but we've already encountered the problem. What if we need a cumulative probability? What if we need a cumulative probability? Okay, so here's how we do it if we need a cumulative probability. Right, so that was the question we had a second ago. We had x6 follows negative binomial 0.8, 6, and we wanted to work out the probability it was going to take you more than 10 goes. In other words, cost you more than £25. And it says find the probability that the 6th success doesn't occur until after the first 10 trials. So that means by the first 10 trials, you should have had at most 5 successes. And then the 6th success is going to come sometime later. We don't know when, but it's going to come sometimes later. So what we can do is we can just use our logic to find a way around this problem. Working out probability x6 is greater than 10, which is a cumulative probability, is kind of a bit annoying to do. But we can think about it differently. We can think, okay, we don't want John to win the teddy until after his 10th go. So what has got to happen? That means by the 10th go, he should have had 5 hoops maximum 5 hoops. If that's happened, it doesn't matter how many hoops. If by the 10th go, he's only got 3 hoops, or he's only got 5 hoops, or he's only got 0 hoops. Doesn't matter how many hoops he's got. But if by the 10th go, he hasn't got 6 hoops, he's got less than 6 hoops. He's got 5, maximum of 5 hoops. Then we know that he's going to get his 6th hoop sometime later. Now, in reality, he might just stop playing, in which case he might never get his 6th hoop, but that's okay. We won't worry about that. We won't worry about that. We're just going to say, right, so 10 trials, and he's got to have at most 5 successes. Well, that's a binomial distribution. X follows binomial 10, 0.8, and we want at most 5 successes. X is less than or equal to 5. Well, that's easy to work out. That I can just work out from my calculator. I just go to menu, I go to distributions, I choose binomial CD, so I've got to go down to binomial CD. Binomial CD is number 1 on the second page. Then I go to variable. I want less than or equal to 5 on binomial 10, 0.8. That's what I've got to type in, and then it will work out the answer for me. And so it's worked out the answer is 0.0328. That's the answer to that. The thing that we were trying to work out so hard, there's an easy way to work it out. In general, okay, what's happening here? This is a method and it's quick and it works, and it's bypassing the negative binomial distribution to get there. Okay. Imagine you're at a coconut shy. You know what a coconut shy is? The coconut is on a stick, and you get like a golf ball and you have to throw it at the coconut. If you hit the coconut hard enough to knock it off, then that's one of the coconuts off. You have to get 2 coconuts off the poles. There's loads of poles with loads of coconuts in them because there are loads of people playing at the same time. All you have to do is you get given 4 balls and you have to knock 2 coconuts off with the 4 balls in order to win the prize. That's a negative binomial distribution. Okay. So what I want to do is I want to imagine a different situation. So you want to find out the probability that you're going to knock off the 2 coconuts within 4 balls. So maybe you do it in 2 balls, maybe you do it in 3 balls, maybe you do it in 4 balls. Yeah. And so the negative binomial distribution actually looks like this. The first one is either a hit or a miss. The second one is either a hit or a miss. The third one is either a hit or a miss, or a hit or a miss, hit or a miss, or a hit or a miss, or a hit or a miss. But actually, if you've got 2 hits, then you've achieved it. You only had to knock 2 off to win. So if you've got 2 hits, then you've achieved it. You wouldn't carry on and do these extra 2 branches. You wouldn't carry on and do these extra 2 branches, hit or miss. Okay, now I want to imagine you're playing the game. Okay, so to Shane, you're playing the game. You've paid £5 to play this game. If you get 4 balls, if you get the 2 coconuts off of their sticks within those 4 balls, then you're going to win the prize. The prize is a goldfish. Yeah? Yeah. Are you after a goldfish at all, to Shane?
Sure, why not?
Okay, good. Okay, if you weren't, you're still playing the game, so you just have to throw the goldfish away. I don't know, chuck it on the floor, give it to Joanna, or eat it. I don't know, whatever you want to do. That's from A Fish Called Wonder. Have you seen that program?
No, I haven't.
That film, rather. It's a really wacky film. It's really funny, but it's really wacky. And this guy is like kidnapping someone and he's attacking him, but he's like a crazy nutcase like assassin. And he takes the guy's got these goldfish in the fish, and he says, "Tell me where this thing is." And then he said, and the guy won't tell him, so he picks up the goldfish and then he eats it like that. And then he's got more goldfish. He goes, "Don't eat my goldfish! Don't eat my goldfish! I love my goldfish! Don't eat my goldfish!" And so he's eating his goldfish. It's just really wacky and funny. Okay. So right, pay your £5 to play. Just point towards the camera with £5.
£5.
Thank you. Okay, here's your 4 balls. There's your 4 balls. Okay, throw your first one. Wow, that was a very gentle throw. It was a hit, strangely enough. Okay, so you've knocked 1 coconut off. Carry on, throw your next ball. Oh, you missed. Oh, you missed. Okay. Throw your next ball. Oh, you hit. So now you've won the goldfish. But you've still got 1 ball in your hand. What will you do with that remaining ball?
I don't need it because I've won the goldfish.
But you probably didn't really care about the goldfish that much anyway. You were just doing it to show off.
Sure, so I'll throw that as well.
You just would, wouldn't you? I would as well. I would just do it. I would just throw the last one anyway. So the negative binomial distribution would still work if you carried on throwing it, as long as we remember that you got your prize. Whatever happens on that last ball, you got your prize. So what happens here is we're carrying on the negative binomial distribution. We're saying even on the, so what we're doing is we're doing, hit, miss, hit, miss, hit, miss. We're doing all 4 balls. I can't fit them all in because I don't have enough room. Here you got 2 hits. So whatever happens after here, all these branches after here, we're including them. And so it gives us the same probability as getting 2 hits. Here you got a miss, a hit, and a hit. So there you only just achieved it there. Here you got a miss, a hit, and then you got a hit. So whatever happens after this second hit, you're going to achieve the goldfish. But we're carrying it on. So what we're doing is we're taking the whole binomial distribution of 4. We're saying binomial distribution, x follows binomial 4 comma, what's the probability of you hitting it is, I don't know, 0.8, we'll say again. And we're saying once you've achieved 2 hits, probability, the number of hits is, if you've achieved 2 hits, so 2 hits, or if you've achieved 3 hits, or if you've achieved 4 hits, all of those are going to count. So probability X is greater than or equal to 2. So it doesn't matter how many goes you have. We can just carry on our binomial distribution. We can say, as long as you've achieved 2 hits or 3 hits or 4 hits, we can still work it out. So that's effectively what we're doing. We're bypassing the negative binomial distribution, and we're looking at a longer tree diagram, which is a binomial distribution. A negative binomial distribution is a tree diagram like a binomial distribution, but one that's just had some of the branches erased. And we can just ignore the fact that those branches have been erased. Okay, so if you have a negative binomial distribution and you want to find the probability XR is greater than N, then what we can do is use the same binomial distribution, whatever that is, put it into a binomial distribution, and then we're going to find probability X is less than or equal to R minus 1. So we'll do an example to show that. Okay, so you've got X4 follows negative binomial 4, 1, 6. We want to find the probability it takes us more than 8 goes to get our 4th success. So that could be 9 goes, 10 goes, 11 goes, 12 goes. If we use the negative binomial distribution, that's going to be a lot of calculating. But we can skip that by saying, let's use a binomial distribution. Which binomial distribution are we going to use? Well, this is N. So we're going to use X follows binomial 8, 1/6. And then what are we going to find out? Well, this is R. This is R. And we're going to have to find out probability X is less than R minus 1, less than or equal to R minus 1. So that's a 6. And then we're going to find out probability X is less than or equal to R minus 1, R minus 1, 4 minus 1 is 3. So that, which you can work out from your tables, will answer that. Okay, so that's how you do it. Let's have a go at another one. Okay. So we want you to get your 5th success in, well, more than 10 goes. Look, that's not quite the right format. In greater than or equal to 10 goes, but it should just be greater than. Let's change that. Let's change that to probability X5 is greater than 11. That's the same. Greater than or equal to 10 is the same as greater than 11. You know that because you know how to draw a number line. Okay. Now this matches this. Now this matches this. Tell me how to work this out. On X5 follows negative binomial 0.24, 5. I want to work out this. But I've rewritten it like that. X5 is greater than 11. Tell me how to work it out. I don't need to use a negative binomial distribution. I can just go to a binomial distribution. What binomial distribution would I have to use? What would N have to be? What would P have to be? And then what probability would I have to work out? So tell me what goes in there. Tell me what goes in there. And tell me what goes in there. I'm asking that to Joanna.
This isn't stuff from like 5 minutes ago, right? Because I had to go out the room before. So.
Oh, can you tell me when that happens?
Oh, because I had to fix my charger, sorry.
Okay, but just say to me, oh, I just need to pop out for a second.
Okay.
Then I know. Devansh.
Would that be 11, 0.24?
11 and 0.24. 11 is just that number there. It becomes your binomial distribution. And then what do you want to work out?
X is greater than,
No,
is less than.
So when that is like that, this is what you're going to work out.
Oh, less than or equal to 10?
No. R minus 1.
Oh, that was
minus
4.
1. R
4.
minus 1. Okay, so that's what's going to work that out for you. Why that works is complicated to understand. If you can understand it, it's great. If you can't understand it, don't worry about it. Okay. All right, so this is now saying, well, what if I want probabilities on YR, not on XR? XR is actually better for finding probabilities. So If I want properties on YR, so Y5 follows negative binomial 0.4, 5. Okay, so that means our probability of success is 0.4. And we want to get 5 successes. We want to achieve 5 successes. And they're asking us the probability that we'll get our 5th success on the 6th failure. Y is the number of failures. So they're asking us what's the probability that we'll get our 5th success after the 3rd failure. So what's the probability we'll get our 6th success after the 3rd failure? Okay, so again, what we're going to do is we're going to just wipe back a second. We're just going to wipe back a second. Where are we up to at the moment? Okay, up to at the moment, we've had 3 failures, but we haven't had 5 successes. We've only had 4 successes. So this is the moment before glory. This is the moment before glory. The moment before glory is where our glory is the 5th success after 3 failures. This is the moment before glory. We've had our 3 failures, but we've only had 4 successes so far. So we've had our 3 failures and we've only had 4 successes. That's the moment before glory. Well, that must be a binomial distribution, binomial 7, 0.4. Why 7? Because we've had 4 successes and we've had 3 failures. So that means we've had 7 goes altogether. And the probability of having 4 successes, probability x equals 4, means that we're at the moment just before this, the moment before glory. The moment before glory. Glory is getting the 5th success after 3 failures. So far, we've got our 4th success after 7 goes, which also means 3 failures. And then after that, we just need to multiply it by 0.4 to get the final 5th success after 3 flops. So let me just show you what that means. So probability of success is 0.4. We want the 5th success after 3 flops. So that means on the first 7 goes, we should have had 4 successes. Not quite 5 yet, because it's the moment before glory, which is binomial. 7 goes, 4 successes is that probability there. And then finally, on the 8th go, we want to achieve the 5th success. So on the 8th go, we want to achieve the final success. And so there's our probability. Okay. So probability of success is 0.35. We want to achieve our 4th success after 6 flops. So go to the moment before glory. Glory is getting your 4th success after 6 flops. Yeah. That might sound a bit rubbish, or you had 6 flops before you got your 4th success, but for us, that's brilliant. Glory is getting our 4th success after 5th flops. Let's go back to the moment before glory. What's the moment before glory? We haven't got 4 successes, because 4 successes would be glory. So we've only got 3 successes, but we've had all of our 6 flops. It's the moment before glory, because we're not going to have any more flops. Yeah? So moment before glory, we've only had 3 successes, but we've had all of our 6 flops. That means we've had 9 goes so far. We've had 9 goes so far. And out of those 9 goes, we haven't quite had 4 successes yet. We've only had 3 successes, 0.35, probability x is 3. That's easy to work out. That's the moment before glory. You've got 3 successes, not quite 4, but you've used up all your flops. So out of your 9 goes, you've had 4 flops, you've had 6 flops. You've used up all your flops. Now the next moment is going to be glory. So times that by the probability of on the last go getting the final success, times that by 0.35, and then that will give you the answer that we're after, probability that you'll get your 4th success after 6 flops. Okay, so what distribution do I need to use? And what's the probability I need to work out? And then after that, after I've done that, I'm just going to multiply that. After I've done that, I'm going to multiply that by 0.75. This is the moment before glory. You've got to take me to the moment before glory, and then I'll do the final bit, which is multiplying by 0.75. Multiplying by 0.75 will give me glory. Take me to the moment before glory. What's the moment before glory? Glory is achieving your 8th success after 4 flops. What's the moment before glory, Tashane?
after 7.
So Glory is achieving your 8th success after 4 flops. So tell me the moment before Glory, what's happened? Tell me everything that's happened. How many successes have I had? How many flops have I had? The moment before success. Glory.
Had 4 flops and 3 successes.
Yes. So I've had. So Glory is getting your 8th success on the after 4 flops. Glory is getting your 8th success after 4 flops. 8th success after 4 flops. Take me the moment before. You're right to say I've had 4 flops, but how many successes have I had?
You would have had 7 successes.
Yeah. 7. The moment before Glory. Glory is your 8th success after 4 flops. The moment before Glory is, well, you've had all your 4 flops, but you haven't quite had all your 8 successes because you're in the moment before Glory. You've only had 7 successes. So 7 successes and 4 flops makes a total of how many, Shane?
11.
11 goes. And the probability of a success on each go is 0.75. And remind me again, how many successes had I had so far?
7.
X equals 7. So probability X is 7 on binomial 11,0.75 will take me to the moment before here, and then you just multiply by the final success, which is 0.75. Okay, John won the stuff, Teddy. Now he's found this vending machine. There are 4 different toys, equal numbers of each toy. You put 50 pence into it, turn the handle, and a random toy is dispensed. John is after the key ring. Okay, so the key ring is one of 4 possible toys. So the chances you're going to get the key ring is only a quarter. The chances you're going to get the key ring is only a quarter. John's after the key ring. The chances he's going to get the key ring is only a quarter. He needs to get 5 of them. He needs to get 5. You know, this actually happened. This actually happened. We were kids at the time. And you know these gumball machines? They used to have them outside every sweet shop. And one day we were walking home from somewhere and he had like 50p. He put it in the machine and he rolled it. And this keyring came out. And he goes, oh, that keyring's really cool. He really liked the keyring. And I looked at it and I go, yeah, that is a cool keyring. And so he put in another 50p to get another one of the keyrings. But another keyring didn't come out. Something else came out, which was like some sticker or something like that. He goes, oh, I don't want that. He gave it to me. He put in another 50p. And again, something else came out, like a bubble gum came out. And he goes, oh, I don't want that. He gave it to me. And then he goes, I haven't got any more money. And he goes, oh, but I want the keyrings. So this was at the sweet shop at the end of our road. We ran back up our road. He went to his brother's bedroom and his brother had this big jar which he kept loads and loads of coins in. He tipped out all the coins from there. He stuck them in his pocket. We ran back to the machine and he kept stuffing in 50p's into there to get more and more of these keyrings. But actually, I mean, in my example, there's equal numbers of all the toys. The keyring was obviously a very nice prize on that one because not many keyrings came out again. We got loads of other stuff, but not many keyrings. He spent all the money in his pockets, which he'd taken out of his brother's jar. He was like an addict. I said to him, stop. You can't you're just feeding money into this machine. He was like a gambling addict, and he wasn't even gambling. It was just like these gumball machines. It's actually happened. And it was shocking for me because we were 9 and 10 at the time. And I was like shocked by how addicted he was to this machine. He was like, no, I'm not stopping. He kept on and on putting money into it to win it. John was my next door neighbor. And then he got home. He'd spent all the money from his brother's jar. Obviously, later on that evening, his brother came home from work, goes, where's all the money from my jar? And then his brother would have had a right go at him. Probably he would have got in trouble over it. But at the time, he wasn't interested in how much trouble he was going to get over it. Okay. All right. As each prize is dispensed, he examines it. And if there isn't the keyring, he casts it aside, which basically means I get to keep it. What's the probability that I end up with twice as many prizes as him by the time he's finished his mission? So Y5 is going to be the number of flops until he gets 5 keyrings. Until 5 keyrings. A keyring is a success. Y5 follows negative binomial Well, the chances of you getting a keyring, well, there's 4 different toys, is a quarter. And he needs 5 of them before he's going to stop. Okay. It says, what's the probability that I end up with twice as many prizes as him? We want the probability that the number of flops is twice the number of successes. So we want the probability that Y5 is equal to 10. That means he got his 5 keyrings, but in the process, I won 10 other prizes that he just simply threw away. Yeah, I got 10 other prizes. So now we're defining the number of flops. Instead of before, we were just defining the number of goes. XR is the number of goes, YR is the number of failures. Now we're defining the number of failures. We want the probability that he gets his 5th success on his 10th, after 10 flops. We want the probability he gets his 5th success after 10 flops. So that's glory. Glory is him getting his 5th success after 10 flops. Take me back to the moment before glory. What's happened so far? The moment before glory. Glory is his 5th success comes after 10 flops, 10 discarded prizes, 10 prizes that I got given. And then after 10 prizes that I got given, along the way, he won some prizes, but he hadn't won all 5. And finally, glory is he wins his 5th keyring. But at that moment, he's cast aside 10 gifts, which I've taken. Take me to the moment before glory, Joanna.
4 successes.
You haven't given me a lot of information. You've given me minimal information. Why are you being so mean with your information?
9, I think, flops, is it?
Okay, so 9 flops and 4 successes you think is the moment before glory?
Yeah.
Are you sure?
When you get the 5th success on
So
the
what
10th.
happens? Okay, so what happens? You've had 9 failures so far, which means 9 discarded prizes for me. You're John, okay?
Okay.
And I'm me. Because it's easy for you to play me. No, actually, you play me and I'll play John.
Okay.
Okay? You're me and I'm John. Right? What am I after?
What are you?
Yeah, John. What am
yeah.
I, John, after?
Yeah, you're John.
I'm John, yeah. So what am I after?
Oh,
I'm John and you're me. So whenever I say me, I'm talking about John. And whenever I talk about you, I'm talking about me.
yeah.
Okay?
Yeah. I don't remember what the thing was that you're trying to win.
It's key rings.
Oh, yeah.
What's John after?
Key rings.
No! What's John after?
5 key ring.
5 key rings. The negative binomial distribution is always to do with achieving a set number of successes. It's not just a key ring. My God, if it was just a key ring, when we walked past that shop on the way home and he put the coin in and he got the first key ring out, we would have been done if that's all he was after. Oh, I've got a great key ring. I'm not going to come back to this fruit machine again. It would have all been over. Yeah. But he was after 5 of the key rings. He wanted loads of them. Okay. So, right. So, what's the moment before glory, Joanna? Glory is when you have got 10 prizes that I discarded. You've got them. And I've got my 5 key rings. I've got the 5 key. I'm John, remember? I've got the 5.
Yeah.
Glory is only that moment. If I get my 5 key rings and you don't get any prizes along the way, that's not glory. Do you understand what glory is?
Yeah, like victory.
No. Do you understand what glory is in this case?
Yeah, you got 5 key rings and I get 10 prizes.
Yeah, if you've only got 3 prizes and I've got my 5 key rings, that doesn't count as glory for this question.
Yeah.
Yeah. Glory is you need to get 10 prizes and I need to get 5 prizes. But remember, once I get 5 prizes, I'm stopping. I don't care. I'm stopping. I've achieved my success. I'm stopping. Yeah. What's the moment before glory?
When I've got 9 prizes.
And how many have I got?
You haven't got 5. I don't know. Just
Okay,
know
but
you haven't
it's
got
the
five.
moment before glory, so you're gonna have to give me a number.
I don't know. 3.
Okay, so I've got 3 and you've got 9, and this is supposed to be the moment before glory.
Yeah.
Right, now we put the final coin in the machine, because remember you told me this is the moment before glory. We put the final coin in the machine, what comes out? Tell me if it's a keyring or a non-keyring.
A non-keyring is my prize.
A non-keyring, yeah?
Yeah.
So that's for you, yeah?
Yeah.
Okay, so have we reached glory now? How many have you got?
I've got 10.
Well
so,
done.
Yeah.
How many have I got?
You haven't got 5, so you haven't won.
So have we reached glory?
Oh, do we both? Oh yeah, we both have.
Glory is glory. It's when I've got my 5 and you've got the 10. That's glory. Nothing
So,
else is
okay.
glory.
So then the moment before glory is you got 5 key rings and I've got 9 prizes.
Okay, are you sure about that?
Yeah, because then only one of us can get.
If once I've got my 5 prizes, glory or no glory, I don't care. I'm not carrying on putting money in that machine. You know that. Once I'm John, all I'm after is the 5 key rings. I'm single-minded now. Yeah, I'm like a drug addict. I don't care about anybody else. I just care about those 5 key rings.
So then maybe I've got 10 prizes and you've got 4 key rings.
Lovely. Now you understand the moment before glory. The moment before glory is you've got your 10, which are basically my failures, aren't they?
Yeah.
And I haven't got my 5. I need to get my 5th one, because that will be glory then. Yeah, I haven't got my 5. I've got 4. I've got 4. I can't have 3 because that wouldn't be the moment before glory. I must have 4, but not 5. Yeah.
Yeah.
Right. So tell me, the moment before glory, how many 50p's have we put in that machine so far? The moment before glory.
It's 50p per prize, right?
50p per go.
And I've had 10 goes. I think.
You've had 10 prizes and I've had 4 key rings.
Oh, so 14.
14.
So then 14 times 0.5.
Times a quarter. So far we've had 14 goes on the machine, and each go has got a probability of a quarter of achieving a key ring. And how many key rings have we got so far?
4.
4. So that's the moment before glory. So this is the moment before glory. What should we times that by now to get glory? What's going to happen on the next go? This is the moment before glory. Now take us to glory. What's going to happen? Next go, I'm going to put the 50p in. What's going to happen?
You're going to get your key ring.
So times the probability of a key ring. Times the probability of a key ring. Well, the probability of a key ring is quarter, times a quarter. So times it by a quarter to give me my key ring as well, my final key ring, and that's the probability we want. Yeah. This you can stick in your calculator. So you can stick that in your calculator. You go to binomial PD, which is number 4, and you say type in variable, and then you just type in this. You type in 4, and then 14, and then a quarter, and the calculator will do the rest of the work for you. 4, and then 14, and then 0.25, just like that. That will work out this. That will give me the answer. So is that the answer to the question? Is this the answer to the question, Joanna? Is working out this the answer to the question?
I don't know.
You got to multiply it by a quarter because that's the moment before glory. What is wrong with you lot? So you've got to times that by a quarter. So it's 0.22, and you've got to times it by a quarter. So that's going to be, well, 0.0505. 0.05, roughly. Okay, 0.055 is going to be our probability of success. You can work out the moment before glory by using the binomial distribution, and then the final bit, you have to multiply it by the final thing. What's the final thing that's got to happen? It's always got to be one more success. Why? Because the moment before glory is you haven't got all the successes yet. You're one success short. That's what we mean by the moment before glory. Okay. Phew. Okay. He says he doesn't care even if he wastes £5 on discarded coins. what's the probability he wastes more than £5 before he's satisfied? So it costs 50p a go, and we want the probability he wastes more than £5. So y5 equals number of wasted presents, wasted 50p's until 5 key rings. Y5 follows negative binomial a quarter comma 5. Okay, right, we want him to have wasted £5. Well, at 50p a go, that's 10 lots of 50p's. So we want probability y5 is greater than 10. We want the probability that y5 is greater than 10. But again, that's really hard to work out. It's a cumulative probability. So how do we work out cumulative probabilities? Well, here's how we work out cumulative probabilities. To work out a cumulative probability, we use this. Actually, you know what? I'm going to tell you the easiest way to do this is to just redefine it. Just redefine it. Say, instead of having y4 follows negative binomial a quarter comma 4, just change it to x4. Change it to x4 follows negative binomial a quarter comma, well, you just add that number to it. So instead of being 4, so that's going to be 4, a quarter comma 4, and then probability x4 is equal to, well, this was 6, you just got to add 4 to it. So x4 is greater than 10. So to change it from y4 to x4, remember what we did when we looked at the graphs. When we had the graph of y4, if we wanted to get the graph of x4, we had to shift it right by 4. So all the numbers had to move right by 4. So all the numbers had to move right by 4. So that's probably the quicker and easier way of doing it, okay? And then now we can say, yeah, we're going to use x4 is greater than 10. So we're going to use x follows binomial 10 comma a quarter. I'm going to work out probability x is less than or equal to r minus 1, 3, like that. So we can work it out like we did the previous ones. I'm using the same rule as we did the previous ones. Okay, this time I'll use the rule for y4 just so that we know how to use it. Okay, so this is this probability. Okay, and so f is that number there. So, well, actually ours doesn't say it's greater than f, so why don't I change it? It says y3 is less than or equal to 2. So why don't I change that to 1 minus probability y3 is greater than 3. Then that's that probability and that probability is the same, because the number line would show you that they're the same. You know on the number line that they're the same. Okay, now this looks like this. So this number here is f. Okay, so this number here is f. Okay, so what I have to use is I have to use the negative, but I have to use the binomial distribution. X follows binomial n comma p. But what is n? This isn't n, this is f. This is f. So what is n? N is r plus f. N is r plus f. So it's that plus that. So n is 6. So n is 6. R plus f. That number plus that number added together. So it's 6. P is still a third. And then we want to find probability. X is, it says y is greater than that. And so we have to change that to x is less than or equal to r minus 1. X is less than or equal to 2. Okay, but remember, we were working out 1 minus this. So we need to 1 minus that, because that is that. Okay, so that's how you'd work it out on there. Okay, so that's how to work out probabilities. And if you need to work out lots of probabilities, you need to use a cumulative distribution. Next thing you want to ask is, how do I work out the mean and the variance? Is there a quick way to work out the mean and variance? Well, if we're talking about XR, then the quick rule for the mean is just R over P, this divided by this. And the quick rule for the variance is RQ over P squared. So that times Q, well, if P is 0.3, Q would be 0.7. So R times Q divided by P squared. A pollster asked couples to fill in a questionnaire. He needs to get 10 forms filled in, but the chance that any individual couple will agree to take part is 2/3. Okay, so let's define what X is going to stand for. Right, we need 10 forms filled in, so X10 equals the number of people I have to ask, number I ask until 10 filled in. Okay, number of people that I have to ask until I get 10 filled in. X10 follows negative binomial. The probability of getting a filled in is 2/3, and 10 is the number that I need filled in. Okay, it says, what is the most likely number of couples I have to stop? What does that mean? What does the words most likely mean when we're talking about a distribution, Devansh?
The mode.
It does mean the mode. It doesn't mean the mean. It doesn't mean the median. It means the mode. So how do we find the mode? Well, we learned how to find the mode before. We said that it was Q over P times R minus 1. Q over P times R minus 1, which is, well, that's P. So it's going to be 1/3 over 2/3 times R minus 1 times 9, and then rounded down, So that's going to be 1/2 of 9 and then rounded down. So that's going to be 4. That's going to be 4. Hold on, no, that's not right. We were always drawing Y10, not X10. We said it's easier to draw Y10 than X10. So the mode of Y10 would be 4. What would the mode of X10 be? What was the translation I had to do to Y10 to get X10? To Shane.
I don't quite understand what you mean.
When we were doing the graphs, back in the day, when we were doing the graphs, way back here, when we were doing the graphs, this was Y4, which was negative binomial 0.4, 4. Y4 starts from 0. So it's much more like a binomial distribution. Binomial distributions start from 0. Poisson distributions start from 0. But the negative binomial distribution only starts from 0 if you define Y4, not X4. This is a graph of Y4. If somebody wants to know what a graph of X4 looks like, it's easy. You just shift it right by 4. There you go. This is a graph of, it's still Y4, so I'm not going to do that one because it's a bit boring. Here's a graph of Y8. 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 If you want to know what X8 looks like, this is Y8. If you want to know what X8 looks like, you just shift it across by 8. There you go. That's what X8 looks like. What was the mode of this one? The mode of this one, Y8, was, well, it was both of these were the mode. So it was 6 and 7. What's the mode of this one? Well, we shifted it across by 8. So 6 plus 8 is 14 and 7 plus 8 is 15. So the mode of this one will be 14 and 15. It's easy if you know the mode of this one to find the mode of this one. Here we go. This is Y12. This graph here is Y12. If I want to find X12, what do I need to do? Shift it across by 12. That's it. Shift it across by 12. Easy. What was the mode of this one? The mode of this one was 10 and 11. What's the mode of this one going to be? We just got to shift it across by 12. 10 plus 12 is 22. 11 plus 12 is 23. 22 and 23 will be the mode of this one. It's easy to get from one graph to another. And when you slide the graph across, you slide the mean across, you slide the mode across, you slide the median across. They all just slide across. Easy. So when we were doing this question here, and we were trying to figure out I do apologize. We've gone over, like we're supposed to finish by 9. And when we finish in the classroom, I really do try hard to finish at 9. I know I'm still not that successful, but I do try hard then. But I don't even try anymore because I just think, well, you're at home. It's not like anybody's waiting outside for you. But I do realize that some of you might be waiting for, like, your dad might expect you to do something, or your mum might expect you to do something. So I do apologize. I keep overrunning, and I don't really fuss about it too much, but I do realize it's quite, it does go on a bit long sometimes. Okay, so we found the mode. We didn't, this method to find the mode doesn't give you the mode of x10, it gives you the mode of y10. So we've worked out the mode of y10, not x10, but we weren't supposed to be working out the mode of, we had x10 here. Look, this was our definition, it was x10. What's the mode going to be for x10 then, to Shane?
We need to shift it by 10.
The mode for this one, y10, is 4. So if you shift it by 10, what are you going to get?
It'll be 14.
14. So the mode is 14. Okay, how do you find the median? Well, so how do you find the mean? How do you find the mean is you just use this rule here, R over P. R over P. What's my distribution here? It's 10 over 2/3, which is 30 divided by 2, which is 15. So the mean is 15. You'll often find the mode and the mean are either the same or just one number apart from each other. They're either the same or they're one number apart from each other. Now, this is the tricky question. How do you find the median? How do you find the median? Well, the median is always between the mode and the mean. So we know the median is either 14 or 15 because there's no other numbers between 14 and 15. If we had the mode as being 10 and the mean as being 20, then the median might be 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Although realistically, it will probably be closer to 15. Yeah, because it will be in the middle of them. So probably it's unlikely to be 10 and it's unlikely to be 20, but it might not be 15. It might be 14 or it might be 16. It might even be 13. It's unlikely, but it might be 13. But the median is sort of going to be in the middle between the mode and the mean. But in our case, our mode is 14 and our mean is 15. So all we need to do is to decide, is the median 14 or 15? It's got to be one of them. So if we try 14 and it turns out not to be 14, it's got to be 15. And if we try 15 and it turns out not to be 15, then it's got to be 14. Well, the way that you try a median, is you say, if I think that the median is 14, if median is 14, that's, in other words, that's Q2, then probability x is less than or equal to Q2 should be Q2 should be just above 0.5, 0.5 just above. It should be just above 0.5. It should be just above 0.5. The problem is, that means I need to find probability x is less than or equal to 14 on this distribution here. And that's again a cumulative probability. So we know if you want to find that cumulative probability, well, first of all, rewrite it as probability x is greater than 15. And then this is the rule. You can just look up the rule. The rule is here. The rule is here. Hold on, I missed it. The rule is here. Where is it? The rule is here somewhere. Here's the rule. Once you've got your negative binomial distribution, you've got probability x is greater than a number. It's got to be probability x is greater than a number. Then all you're going to do is use that number for your binomial distribution. And then this number here, you're going to minus 1 from it, and you're going to do f of that. You're going to minus 1 from it, and you're going to do f of it. Why? Don't worry about it. Don't worry about why. If you don't understand why, don't worry about it. If you do understand why, that's even better. Okay, so all we're going to do is, all we're going to do is just do, so x is greater than 15, so that's going to be our n. So let's change colors. I can't change colors anymore. Let's change colors. X is greater than 15, so that's x follows binomial 15, comma, What was the probability? What was the probability? What was the probability? What was the probability? It was 2/3. 2/3. And we want probability x is less than or equal to, what was R, 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 10. R was 10. We want probability x is less than or equal to 10. Okay, so I'm going to work that out on the calculator, which is just F10. And if it comes out to being less than 0.5, then that's not the median. If it comes out to being just above 0.5, then it should be the median. Let's have a look. Okay, so I'm on PD, so I need to go to CD. So menu, binomial, binomial CD, and I want variable, I only want one answer. And I want less than or equal to 10 on binomial 15, 2/3, 15 and 2 over 3. And it gives me the answer. Okay, that's well above 0.5. So that's well above 0.5. Well, seeing as I said, it could only either be 14 or 15. If 14 is already above 0.5, then it's got to be 14. So 14 is the median. Okay. Remember, the negative binomial distribution is a lumpy distribution. It goes up in big lumps. So you're never going to get it equal to exactly 0.5. It's going to go 0.4, 0.48, 0.59, 0.63, like that. It's just going to jump past numbers. So it's a lumpy distribution. Okay, how do you find the mean and variance if you've got YR, if it's defined in the form of YR? Well, here are the formulae. Again, you just remember the formulae. So here are the formulae, RQ over P or RQ over P squared for the variance. And so in this case, it says he's realized he makes more money if his students fail. So he's a driving instructor. He realized he makes more money if his students fail. So he's tweaked his teaching so that the chance of the students passing a test has dropped from 0.75 to 0.6. He currently has 6 students. How much extra revenue is his clever pan generated if on average he charges up to £2.50 for each extra attempt? Okay, so he's got 6 students. So X6 is the number of test attempts until all 6 have passed. X6 follows negative binomial. Negative binomial. The probability. Okay, the probability's changed. It was 0.6, 0.6, comma 6. But now it's changed. X6 follows negative binomial 0.75, comma. No, it was 0.75 rather. It was 0.75, and he's made it worse. He's made it worse. He's made it harder for them to pass. 0.6 to pass 6. Okay, right. Well, we're not interested in how many goes it takes. We want to know how many flops. How many extra flops did he generate? So let's change it. Let's not define X6. Let's define Y6. So let's define Y6. Let's define Y6. And Y6 is the number of failures, number of failed attempts until. Okay, so this was the old distribution. Let's work out how many failed attempts on average he used to get before. Here's our equation, RQ over P. So that's going to be 6 times Q over P, times Q is 0.25 over P is 0.75. So that's 1 over 3 times 6, so that's 2. So before, there used to be an average of 2 failed attempts. How many failed attempts are there now? Again, we've got to do RQ, so over P, so that's P over Q, 0.6 over 0.4 over 0.6 times 6. So Q over P times R, which is 2/3 times 6, which is, well, 4. So there used to be an average of 2 failures. Now there's an average of 4 failures. So that's 2 more failed attempts. he gets 250 for each failed attempt. So that means £500 more he's making. Okay. And then these are just examples. How do you define what's happening in each situation? In a school fete, a game involves a dartboard with an enlarged bullseye. The average thrower has a 20% chance of hitting it. You pay £1. Your aim is to get 2 darts into a bullseye. If you manage to do this in less than the average number of throws, then you win back your £1. If you manage to do it in less than a quarter of the average, you'll win back your £1, but an extra £5 on top. Would you play or would you not play? So this is a complicated question because it's not a negative binomial distribution. It's not a binomial distribution. It's a make up your own distribution. The things that can happen is you can lose your £1. The things that can happen is you can gain your £1 back. So you win nothing overall. And the other thing that could happen is you win £4. You get £5. Oh no, and you get your £1 back. So you win £5. You win £5. You get your £5 plus your £1 back. So you get £5. How could this happen? What are the probabilities for each of these? Well, what's the probability? Let's start off with the probability that you win the £5. Okay, so if you manage to do it in less than the quarter of the average amount of goes, okay. What's the average amount of goes? You have to get 2 darts in the bullseye. So you stop when you've got 2 darts in the bullseye. So X equals number of goes until 2 bullseye. X2 follows negative binomial. What's the probability of getting a bullseye? It's 20%. 0.2, 2. Okay, so that's the distribution. What's the mean of that distribution? Well, we know the mean of that distribution. Well, if it was Y2, the mean would be Q over P, so 0.8 over 0.2 times R times 2. So that would be 4 times 2, which would be 8. But because it's X2, you've got to shift it to the right by 2, so it's going to be 10. So on average, it's going to take 10 goes. On average, it's going to take 10 goes. So these are the people, the £5 people are the ones who do it in less than a quarter. So they do it in less than 5 goes, less than 5 goes. These are the people who do it in, if you manage in less than the average number of goes, you win back your £1. Okay, if you do, so this is between 5 goes and 10 goes, not including 10, up to 10. 5 to 10 goes. This is X is between 5, including 5, and not including the 10. And this is whatever the rest is. This is the rest. Okay, so what we need to do is we need to work out probability X2 is less than 5. So we need to work out the probability X2 is less than 5. We know how to do that, and then we're going to put it in there. Then we need to work out the probability X2 is between 5 and 10, and we can put that in there. And then finally, we can do 1 minus these two and then put that in there. And then we can do that times that, that times that, that times that, and then we'll have the expectation. So here we're having to do a lot of work before we get to the answer. The victor is the first to win 4 games. So this is best of 4. Now give me, if I say to you best of 3, how will you know when you've won? Best of 3. So we're going to do paper, scissors, rock, paper, scissors. And we're going to do best of 3. How will you know when you've won, Devon?
When I've won 2 games.
When you've won 2 games. So best of 3 means you've won 2 games. So in actual fact, you could say, instead of saying best of 3, you could just say, okay, when you've won 2 games. So this is win 4 games. This is the first one to win 4 games. So first one to win 4 games would be best of how many?
3.
No. When it was best of 3, you said that was 2 games.
Yep.
So if you win 2 games, you've won in a best of 3 competition.
Yeah.
If you win 4 games, what have you won in a best of how many competition?
Oh, best of 5.
No, best of 7. Where are you making this up from? If it's best of 5, then when you've got 3 wins, you've won. You wouldn't have a 4th win ever.
Yeah.
Okay.
Yep.
So this is best of 7. So this kind of situation here, you can just deal with it with a binomial distribution. You can say, okay, best of 7. You can say n is 7. You can just say, imagine that n is 7. Imagine that n is 7. Now the thing is, this isn't binomial n is 7. Binomial n is 7. You have to carry on for the 7th go, no matter what. Yeah. So let's play rock paper scissors. Okay. First go, oh, I won. Second go, oh, I won. We're playing best of 7, yeah? Third go, oh, I won. You're not doing very well at this, Devansh. 4th go, oh, I won. How are you feeling now?
Sad.
Okay. Why?
Because I've lost. Because I've lost all of the games.
So far, but you might still win. We're doing best of 7.
Yeah.
You still hopeful?
No, because I'm gonna lose anyway.
Why?
Because you've won 4 games.
Yes. So best of 7 stops when you've reached 4 games. Am I right? When you've reached 4 wins. Theoretically, it could stop after 4 games. It could stop after 5 games. It could stop after 6 games. And it will always stop after 7 games. There's no point where it would go beyond 7 games, is there? So best of 7 has a maximum of 7 games, but it could stop after 4. But what if we played best of 4, so best of 7, and I won the first 4 and we carried on? Would that affect the overall outcome at all if we carried on anyway? So on best of 7, although best of 7 stops after 4 sometimes, if I've won the first 4 games, it doesn't matter if you carry on. It's not going to affect the probabilities if you happen to carry on. Okay, homework. Oh, where's your homework? Oh, the homework was on here a second ago. Where's it gone? Let's look on here, see if it's on here by any chance. Nope, that's not it. Where's it gone? I'm sure it was on here. Probably didn't save it. Okay. Okay, I'll just write it up. Okay, so the homework is going to be, so it's a bit kind of, okay, so you've got 2 different homeworks, yeah? You've got the reduced homework, and you've got the easy and reduced homework. And the reduced homework was exercise 7H 1 to 9 odds, 10 to 18 evens, 19 to 29 odds, and then 31 to 38. And the easy one was the same thing, same as that, same as that, same as that, but now you don't have to go to 38. You only go 31 to where was it? Can't see now. 31 to 33. 31 to 30. 31 to 34. 31 to 34. Okay, that's on that exercise. And then we move on to 7i. 7i. And on 7i, it was the reduced homework was 1 to 6 odds. So 1 to 5 then. 7 to 11 odds, and then 21 no, it's 12, 13 to 18. And for this one it was the same here, 1 to 5 odds, same here, and then you only had to do 13 to 15. Okay, so that's your homework.